Welcome to Brain Vision.
Okay, so I did this problem, except the first time the sound didn't work too well. So I'll re-explain everything step by step and showing it with my cursor where we are. Okay, so the first part of the problem is we want to find out the kinetic energy of the electron after the collision, and we want to know what the speed of the electron would be. And then for the second part, we want to find out what the wavelength of a photon would be within the electron. So we have a photon that collides with an electron that's at rest. And the kinetic energy of the electron changes. So we would use the equation E energy. We would basically use a change of energy equation, which would be hc divided by lambda minus hc divided by lambda prime, where h is Planck's constant, c is the speed of light, and lambda prime are the wavelengths of the photon. So here we have the equation right here, hc divided by lambda minus hc divided by lambda prime, and we can pull out hc from both because they have that in common. So we have hc times lambda prime minus lambda divided by lambda prime, which we get by using common denominators. And therefore, this also signifies that the kinetic energy is equivalent to the energy of the photon. So by knowing Planck's constant, which is 6.626 times 10 to the negative 34 joules per second, and that c, which is the speed of light, equals 3 times 10 to the 8 meters per second, we plug that in. And then we also know the wavelengths, the initial wavelength, and then the scattering wavelength, which is shown by lambda prime. We would plug everything in. So we do 6.626 times 10 to the negative 34 times 3 times 10 to the 8th multiplied by 0.1132 times 10 to the negative 9. We convert the nanometers to meters, minus 0.11 times 10 to the negative 9 divided by 0.11 times 10 to the negative 9 times 0.1132 times 10 to the negative 9. Just a note, this is 10 to the negative 9 is the conversion from nanometers to meters. So that we get a value for kinetic energy of 5.108 times 10 to the negative 17 joules, which is also equivalent to 510.8 times 10 to the negative 19 joules. And then from here, we also know that 1 electron volt equals 1.6 times 10 to the negative 19. So we take our kinetic energy divided by 1.6 times 10 to the negative 19, and we get a kinetic energy of 319.25 times 319.25 electron volts. And then the second part is to calculate the speed, and the speed is, we derive it from the kinetic energy formula, which is kinetic energy equals 1/2 mv squared. Rearranging things, we get v, the speed, equals the square root of 2k divided by m, and the mass of the electron is given to us. Therefore, we plug everything in together, as you see here, 2 times the kinetic energy from the first part divided by the mass, 9.109 times 10 to the negative 31 kilograms. We get the square root of 1.125 times 10 to the 14 joules per kilogram, which when we continue on, we get 1.059 times 10 to the 7 meters per second, and therefore we can conclude that the speed of the electron is 1.06 times 10 to the 7 meters per second. And for the second part of the problem, which is part B, we want to find the wavelength of the photon that is emitted. and that is given by lambda, which shows wavelength. Lambda equals 8c over E. All of these numbers are given to us. H is Planck's constant, C is speed of light, E is the energy, which is also the kinetic energy of the photon. So we plug everything in, so lambda equals 6.626 times 10 to the negative 34 joules seconds, which is Planck's constant, multiplied by 3 times 10 to the 8th meters per second, divided by the kinetic energy, which is 5.108 times 10 to the negative 17 joules. And we get 3.8915 times 10 to the negative 9 meters, but we want an answer in nanometers. So to do that, we will multiply by 10 to the 9, which cancels out the 10 to the negative 9. And we get lambda equals 3.89 nanometers. And that concludes this problem.